Yes. So, we were discussing in the previous class about Diels-Alder reactions. We saw some selectivity about Diels-Alder reactions. Today we will be talking about the reactivity of Diels-Alder reactions, and then we will be understanding much about intramolecular Diels-Alder reactions. Okay. So, we will start with the reactivity of Diels-Alder reactions. For example, like I take a butadiene with an alkene, okay, and do this reaction. Okay, normally it takes 700 degrees Celsius, okay, to do this reaction, and you end up with your cyclohexane. Okay, cyclohexane. So you have your butadiene with alkene, and you see it takes very high temperature, like 700 degrees Celsius, to do this reaction. But if I take my butadiene and if I make my alkene more electron poor, okay, by attaching electron withdrawing group like cyano, you see that the rate of the reaction in 140 degrees Celsius I get the same product. See, there is a rapid decrease in temperature, tremendous decrease in temperature. So, that initially it was 700 degrees Celsius, now the reaction goes in only 140 degrees Celsius. Very another interesting fact is that if I take the same cyclo butadiene, but with a very good dienophile as a very poor, like, yeah, 4 side cyano, all electron withdrawing substituents, okay, and you can see this reaction goes in only 20 degrees Celsius, and you get this very interesting products. See, like if I take my diene dienophile and attach an electron withdrawing group, that means I am making my dienophile much electron poor, and you can see the temperature of the reaction. It starts from 700 degrees Celsius and you can take it to 20 degree Celsius. That much you can change the reactivity of your Diels-Alder reaction by modifying your dienophile. Even you can play around with your diene also. If I have a reaction like an aldehyde, okay, and this reaction if you see is 160 degrees Celsius and it goes in 1 hour, okay, I get my Diels-Alder product. Right. But if I, so how you make your diene much more good for your Diels-Alder reaction? Just you have to attach your electron donating. In the case of electron dienophile, you use electron withdrawing. Here you use your electron donating. So you have an, for example, I take a methoxy and do the same reaction, and you see that the reaction in 100 degrees Celsius in 2 hours gives me my product. So, so the reactivity, that is what the reactivity of Diels-Alder. So, reactivity of your Diels-Alder can be altered by altering your dienophile and diene. Okay. How it happens? Why it should happen basically, or how to understand it? Basically, you can get into your Luhmann HOMO again. Okay. If I say I will take the Luhmann HOMO, basically I will take my regular diene without any substituent, okay, and a dienophile. So, this should be my HOMO and this should be my LUMO, and Dinophile, and this should be my. So, what I am talking about here? I am talking about the interaction of the HOMO of your diene with the LUMO of your dinophile. So, if you are saying this is the interaction I am talking about. Okay, this is your delta E. So, this is the energy difference we are talking about between your HOMO of your diene and LUMO of your dinophile. But in the same case, if I attach a donor, okay, and an electron withdrawing, that is your acceptor moiety, okay, what happens? My donor, my acceptor. If you see what will happen, this HOMO, once I have a donor, the HOMO will lift up with this. And same way your LUMO will come down. So, this is your HOMO, and this is your LUMO of your diene, this is the LUMO, and this is the HOMO of your, okay, sorry, this is your LUMO and this is your HOMO. Okay. Now, you are talking about the HOMO and the LUMO, right. You see now the energy difference. In this case, this is your delta E. In this case, this is your delta E. Okay. So, you can easily see now why the reactivity is C. In the initial case, you had so big an energy difference between your HOMO of your diene and the LUMO of your dinophile. Here you can see once you have a donor, the HOMO energy lifts up, and if you have an acceptor, then the energy of a LUMO comes down, and now the energy gap is very small compared to the initial case, and the reactivity of your Diels-Alder is much more faster. Okay. If you watch this energy diagram much more careful, you can end up in asking one question, is that why cannot I can react the HOMO of my dinophile with the LUMO of my diene? Is it is possible? See, so far we are talking about the HOMO of your diene and LUMO of your dinophile. If I can change this energy difference, you can always say I can lift this up and lift it down. So, the HOMO of my dinophile, is it is possible to react with the LUMO of dinophile? Yes, you have that type of Diels-Alder reaction that we call as inverse electron demand Diels-Alder reactions. Okay, that is what we are going to do now. You can call them as inverse electron demand. Basically, what we are talking about is I have a LUMO, I have an HOMO. This is a diene, okay, with an acceptor molecule. Okay. And if I have a dinophile with a donor which is completely reversed, okay. Now, I can talk about this interaction. This is the HOMO and this is the LUMO, okay, and this is your delta E. So, then it is possible, right. So, I will be talking the interaction between HOMO of my dinophile and LUMO of my diene. Always so far we were talking about the HOMO of your diene and LUMO of your dinophile. Now, it is entirely inverse. Okay. So, this type of reactions are allowed. You can see many Diels-Alder reaction. Okay. By energy diagram it just looks to be fine. Now, we will see that whether it is orbitally allowed, okay, because that we should keep in mind. Okay. So, if you do the again HOMO LUMO interaction for inverse electron demand, or you can people call it as photochemical also. Fine, right now we will call as inverse electron demand. You were talking about the LUMO, we were talking about the LUMO of our dyne. This is the LUMO of your dyne. If I have my OMO of my dynophile, okay. Now you can see again it is allowed suprafacially. You can again have a pi 4s plus pi 2s. So, your suprafacial allowed. So, what it says basically, it says that yes, the inverse electron demand by energetically it is favored, and by if you do orbitally, and it also allowed. So, if you take the LUMO and HOMO dynophile, again it is suprafacially allowed, just similar to your earlier normal DielsAlder reaction. So, we will see some quite interesting reactions of inverse electron demand, some examples of inverse electron demand. Can have your type of systems. People have systems like this with your, now your dynophile as an electron donating substituent. If you just read this reaction, you end up with a chlorine, all the sites of the reactions. You can get this product. Even there are reactions where it has been used. You have been heard about Diels-Alder type of pesticides. You can synthesize using this inverse electron demand reactions. For example, if you take a system like this, and then click in line system, and if I do this reaction, end up with that, and your chlorines. So, this product is interesting in one sense, like you can, it is used as a nice pesticide. So, if you epoxidize this epoxidation, get a very nice product. Okay, so you get this product, and this is called as Diels-Alder, which is a good pesticide. Okay. So, you can using your inverse electron demand chemistry, DielsAlder reactions, you can do this type of DielsAlder reactions. Fine. Now, what we will do is that we will see some examples of heteroatom DielsAlder reactions, okay, which also important one case, like we call as can do that reactions. Heteroatom DielsAlder reactions, where you can have like we were talking about dinophiles all with the carbon systems, right. So, we can think about having dinophiles of oxygen and all this type of systems slowly. So, the you know this reaction, it is a nice favorite, like yeah, we can start with this initially. Okay, with your oxygen type of systems. Okay, this you have no, because you get a very nice product here. Again, I can do my second thing. A double bond here. So, I get like two DielsAlder reactions, okay, were happening. Like two types of DielsAlder reaction you can look for here in this case. This we call as heteroatom DielsAlder. Like yeah, this is not exactly heteroatom, but you can think about oxygen in the systems. But we will see now the exact heteroatom DielsAlder reactions, which are like if I have a this is a proper example for your heteroatom DielsAlder, right? Very good class example. So, if you have this type of systems, so what is the product you look for? This will be your dinophile and dine. So, you can look for right. So, I can look for this type of products. I can have my heteroatom on the other side of my diene. Okay, that also I can take. For example, I can take a system which is have a ketone, okay, and my CCl3 with an amine. Can have this type of systems. Okay, and we can have my YT. This also undergoes nice heteroatom. I have an O. Yes, you make a type of pyrans type of rings structures. This reactions goes in it very nicely. Okay. These are like two good examples of heteroDielsAlder. Okay, we have one more nice example which I have studied on heteroatoms DielsAlder reaction is using your Danishef dienes, right. So, for example, you have like Siler system. My this is my dinophile I am talking about. Okay, this diene you have studied, where you have O Si Ma3. this type of dynes we have studied. We call this as what? Danish sky dye. It has a lot of synthetic utility has been done across this. You can end up with a type of like very nice carbohydrates using this chemistry, Diels-Alder chemistry. You get, this is your oxygen. You can synthesize very few reactions in which Diels-Alder you come across carbohydrate synthesis. This is one of among them. In Danish dye you use, and you end up, if you see the product you are going to end up is will be, because again it gives you a selectivity, sorry, just there is a change in your dinophile. Okay, it should be OBN, there is a CS2, fine. So, you will have a BNO, get a nice carbohydrate, a very novel approach for synthesis of carbohydrates. Okay. And you know it has a selectivity, you can select this, this part, stereochemistry will be selected because of dinophile. So, it is a very novel approach for your carbohydrates. So, that is what you have to, that is why this is very like specifically important, that is why I am taking it. So, these are some, even you can call this as some scope of Diels-Alder reactions, okay, very good scope of Diels-Alder reactions. You are talking about like making, first example you are talking about making two types of Diels-Alder reactions, then you have an pyrene system and nitrogen based ring systems you are creating. Now, you are creating about your carbohydrate systems. You can call as a scope of Diels-Alder reactions, these are all, it has lot of scope. Okay. Now, what we will do is that then we will slowly get into understanding the heteroatom Diels-Alder reactions, that are much more good Diels-Alder reactions, like you should know that intramolecular. Now, heteroatom we have seen, now we will see this intramolecular Diels-Alder reactions. Okay. We will call this as simply IMDA, right, intramolecular Diels-Alder reactions. Okay. For example, we will take the simplest substrate and try to understand them in detail. Okay. I take okay, first we will see what happens here, and do not worry about the stereochemistry right now, first we will see how the reaction goes. So, it is again this will be your dyne, that is your 2 pi electron system, and this is your 4 pi electron system. Okay, this is your dyne and this is your dienophile 2 pi and this is your 4 pi system. Okay, if you eat this you can get your cyclic ring system, like your Declean type of systems, right. Okay, this is your simplest Diels-Alder reaction. So, you have a dyne, you have a dienophile within the system and you heat it, you get your Diels-Alder reactions. The stereochemistry is really interesting because you are trying to fuse a ring, right. So, now you can think about it, whether it is a trans ring junction or it is a cis ring junction, which it is going to favor. Okay. So, the stereochemistry part is very important in understanding this reaction. If I take the same product. Okay. Taking the same product. Okay. Now, if I do this heating, and I will say that the product which we get is a trans ring junction 1, this you end up with that sort of trans ring junction 1. Oh, one. Yep. Oh, sorry, it's there, right? Yeah. The previous example also. So you end up with a trans ring junction. We call this. See how to understand this guy. How to understand that is giving a trans ring junction. See, basically, when you are talking about intramolecular DielsAlder reaction, sometimes you consider more steric than your endo rules. Okay, steric you have to take into consideration. Okay. If I draw the how it transition state, how it looks like, not transition state, exactly steric, in which way it can avoid much steric interaction. If I draw this properly, I can say that can I have a system, I can think about an hydrogen here. This is the hydrogen I am talking about. See, I can think about drawing this in this way, fine, to have a less crowding. So, now you can see when it is fused, this hydrogen is on that way and this is on the other way. So, you end up with a trans ring junction, that is why you end up with a trans ring junction. It is not more about your endo rule, okay. It is more about your steric. So, I have taken, I have drawn this way, there is a minimum steric crowding interaction, fine. So, you get a nice trans ring junction now, clear. Okay. This whole chemistry becomes little bit interesting once you have a carbonyl now. Okay, same system, same DielsAlder. If I have a carbonyl, same substrate, I am taking the same substrate now. This is the same substrate I was talking in earlier case. Now I just have a carbonyl here. Now, if you say that if I do this reaction, okay, yeah, you know what product you are going to get, that is no problem. So, you might, okay, but what junction we are going to talk about here. Okay. Interestingly, what happens is that I get a cis ring junction. See, in the earlier cases, earlier case where it was without a carbonyl, just a system, I was getting a trans ring junction. In this case, when there is a carbonyl, I am thinking I am getting a cis ring junction. This also you can get into it. You can understand again by the same steric and orbital corroding is that. So, again if I think to draw the system, but much in this case in a both lecture form. So, this is the hydrogen I was talking in the earlier case. This is my alkene, okay, and this is my hydrogen. Okay. Now, what happens, my hydrogen is same in both the phase, right. And why this happens? This happens because this carbonyl now have a like overlapping with your alkene, backside overlapping. Okay. That is why it takes this phase and it ends up giving us a cis ring junction because of your carbonyl. Carbonyl can now overlap with your diene taking this system. That is very nice. Okay. If you see of your now alkene intramolecular Diels-Alder reaction, you end up with a trans ring junction. If you have a carbonyl in the system, you end up with a cis type of ring junction, fine. We can make it still looks to be much more interesting in one sense, like if you are taking, see now you have a double bond, okay. I can take a cis olefin, okay, or I can take trans olefin, and we will see what happens in that cases. Okay. Okay, if I have taken this olefin, which is like more like a trans one, cis one, yeah, cis olefin we are taking because hydrogen is hydrogen, yeah, cis olefin we are taking out, and see what happens in this case. Once we do this reaction, okay, we get a product. Yeah, what we have studied that if we are talking about this system should be cis ring junction, okay, but very interestingly you have a CO2 me, okay, that this and this are trans, right. So, you get this type of products. So, you know this you can explain with your end of folding. You have a okay, I have just and I have a double bond here, yes. CO double bond. Oh, sorry, carbonyl is missing there. No, we will take a system without carbonyl. Sorry, just without carbonyl and see what happens. So, how to go about now? Just same way you can understand this if you can think about the end of folding of this. Okay, so I can write my OMe here. Okay, now I can put my hydrogen, see whether I am right. So, you get this interactions and you end up with your trans because of your carbonyl on the other way to your hydrogen. Okay, that is where you can look this much more better to give you a product. Okay. Now, if you do the same chemistry using your transform, your alkene, here to Me and plus my hydrogen. This is CO2 Me. Okay. So, if I do this reaction, you see nicely you end up other way geometry. Hydrogen. So, you are getting a cis type of thing. You know how to draw cis, because we have seen that in cis case how we folded it. Trans case we try to use a chair like conformation. Cis case we were using different way, that is how we thought about cis ways, like pentane type of molecule we were talking. Okay, I am talking about this hydrogen. I have an alkene here. Okay. I can talk about my carbonyl with my OMe, and my hydrogen will be this way. See, this way you can fold up, end of folding, to give you this product. Fine. So, that is that is what you can think about, like if you are doing intramolecular Diels-Alder reactions, like if you have a it has a selectivity. Okay. If you have a diene type of systems, okay, you have to, when you are fusing a ring, you have to see whether it is a cis junction or trans junction. Okay. You can use folding, but you have to keep in consideration your steric. Okay, that also should be taken into consideration. Fine. Okay. So, that is think about your intramolecular Diels-Alder reactions. We will do some examples on that. See how intramolecular Diels-Alder reactions works. We will take the first example. Same example in one way, yeah, but we will just try to see whether we can figure the product out of this. I have done this thing, but with the methyl I want to, can you write the product CO2 Me, heat. Just you have this, I want to heat this. So, can you think about writing the product? See what you are going to do this, if you just slowly look into this reaction, you are creating a 2 CC bond, right, and you are ending up with the 4 chiral centers. Yes. Yeah. So, that is where this particular example is really interesting. So, what we talked about, if you have a trans type of systems, like you can have a same geometry, right. If I have an hydrogen this way, then my CO2 Me also should be on the same. That is what we have studied in our earlier example, right. So, we have a CO2 Me, both should be cis, when you have a system like this, and this junction should be trans, and your methyl should be the same direction of your CO2 Me. Now, we have a 4 chiral centers now. So, this reaction is a one step, very nice reaction. It is a one step where you add making 2 CC bonds, and then you are ending up with the 4 chiral centers. Okay. So, that is very interesting in that part. So, we will take another important, another good synthetic application of your DielsAlder reactions. I will study this extra diol synthesis. I studied this extra. I have seen this compound extra diol. I have studied this. This is a structure, if you want. This is your extra. See, the thing is that it has nice chiral carbon centers, and that is always nice for you. As an organic chemist, you look for chiral centers. Right, this is called as plus extra this compound. If you want to synthesize this compound, okay, there are a number of good ways to do that. We will start. Yeah, we will start our synthesis. There is one electrocyclic reaction. Anyhow, I will teach you that. Okay. So, if we can take this step, for example, this particular molecule OMB, O tertiary butyl, see, this is what we are going to study, this electrocyclic reactions in this after DielsAlder reaction, after cycloadditions. But anyhow, you guys know about electrocyclic already. Right? What happens? Any idea electrocyclic reaction if I take this and ring closure or ring opening? Yeah. So, you end up with a nice ring opening. Yeah, I will explain when we go there. We will study why it is con, dis, all these things. But just right now, we can say that ring opens. Again, we have O tertiary butyl. Okay, now you can see you have a system now which can undergo a type of DielsAlder, right, because you have a very good dyne system here and you have a dynophile. Okay, it can undergo nice DielsAlder reaction. So, what you end up now, you have to fix your stereochemistry also when you are doing DielsAlder reactions. That is much important. That is why your pericyclic reactions are more important, because like it helps you to get your stereochemistry in the right way. Tertiary butyl, you have here. So, you have a ring closure here, you have a system with an hydrogen outside. You can think about this. Okay. So, this you have, then you can always demethylate this to your hydroxy group, that is your estradiol. So, you can also have this OHs here, OH, you have a OH here because you can have nitrogen. That is why DielsAlder. There are many applications which you can think about doing with DielsAlder reactions, and very well known synthetic applications are known using the DielsAlder reactions. Okay. So, these are some synthetic applications of your DielsAlder reactions which you have seen. Okay. So, what exactly to wrap out your DielsAlder is that because that is more important to summarize your DielsAlder, what we did in your DielsAlder. Just I will summarize what we have studied so far in DielsAlder. First we studied it's a nothing but it undergoes cycloaddition of diene, which is your 4 pi electron system, and dienophile, which is your 2 pi electron system. That is what we studied. It is a cycloaddition, and it goes to a transition state. Fine, this is what we studied. Then what we did is that we went to the third important part. We understood this about your diene. We set up two conditions. We found two conditions are necessary for a diene to do DielsAlder reaction. One, it should be electron rich. Another thing which we talked about is that it should be in S cis conformation. See, in case of cyclic acyclic dienes, you have like conformation locked. One, it should be cis or it should be either trans. So, one can be excellent diene, another case it cannot be a diene. But in case of linear system, you always have in equilibrium, like if you take a butadiene, it moves from S cis to S trans, you have all these things. So, that case so your S trans form reacts, S cis form reacts. So, these are the two important conditions, electron rich and S. So, that means what I am saying, your diene should have electron donors or electron donating groups. That is your donor molecules. If they are there, it is nice. That is about your diene. Then we slowly went to a dienophile. The first thing we said that it should be electron poor, right. If it is electron poor, what it essentially means that you should have electron withdrawing group. That is your acceptor molecules. This can be your aldehydes, nitriles, right. These are all very good for that, your dienophile. That is how we made your diene and dienophile. The fifth thing we thought about is your HOMO-LUMO interaction. And we studied that it should be suprafacial allowed in eating condition and the thermal activation or eating condition. So, if you thermally activate, suprafacially it is allowed. So, that is why DielsAlder reaction goes very nice. Okay. that is your about your HOMO-LUMO interaction. Then we went down to the important part, that is about your selectivity, right. We studied about your facial selectivity. It is more like specific, right. The facial selectivity is more like very specific reactions. There we said that we can see in the front approach as well as side approach the whole reactions. After that we worked on our exo endo selectivity. So, in exo endo selectivity we said that endo will be favored because of its secondary orbital interaction. Then we went to regioselectivity and we talked that the electron withdrawing and the electron donating substituents in the product should be either pseudo ortho or pseudo para, this electron withdrawing and electron donating, electron withdrawing and the electron donating. Okay. The electron withdrawing and electron donating, if you see the product, okay, they should be either pseudo ortho or pseudo para in position. That's so that will be regioselectivity, and you can explain this based on your mesomeric structures. Okay. That is we saw about the selectivity. Once we finished our selectivity, then we went about the seventh part, the reactivity. And we say that if we can change your diene, if you put an electron donor on your diene, an electron acceptor on your dienophile, the reactivity of the reaction tremendously increased, and we studied that based on your energy gap, right. So, yeah, electron withdrawing, if you have electron withdrawing in dienophile is good, electron donating on diene is good for reactivity. So, that the energy gap will become less and you can have a nice reaction going on. So, that is about the reactivity we talked about. Then we called as a scope, or we said then we went back and studied the inverse electron demand, which is very important. Okay. In all the cases you were talking about HOMO of your diene and LUMO of your dienophile. In this case we are talking about the HOMO of dienophile and LUMO of diene. So, it is basically HOMO of dienophile with LUMO of diene. Once we did our inverse electron demand, then we moved across the scope hetero-DielsAlder reaction. Then finally, we ended up with talking about the intramolecular DielsAlder reaction. Fine. So, this is the broad these are the areas where we covered on DielsAlder reaction. When we come next class, we will be talking about aldehine reaction. Fine. Okay. That is how we, that is all, we end this class.